Welcome everyone. This is our webinar from King's College London and the H2020 project Restarting Economy in Support of Environment Through Technology. Please do use the Q&A function to ask questions at any time. We'll monitor and respond directly to those questions live, or we'll save them until the end and I'll address them by voice. The meeting is being recorded and will be saved to YouTube unlisted as a resource for FreeStation builders to use. Of course, if the connection breaks, do try and rejoin, or if my connection breaks, then hold on whilst I try and rejoin. Today, we're talking about low-cost, do-it-yourself environmental monitoring for teaching and research. All the slides are available at that link there, the tiny.cc, which I will show you again at the end. And we have a number of speakers, in addition to myself, who are going to cover that ground. This is the overall structure for today. I'm going to give you a bit of an introduction. Andy Britton and his students from a school in West London are going to give 5 minutes on their experience building a school weather station. We're then going to have a couple of interventions from Sophia and Arnout, who are going to talk about applications that they've been involved with of FreeStation, and then we're going to go into practical mode and learn how to build one. So what problem are we addressing with low-cost environmental sensing? The problem is that ground-based monitoring infrastructure has been declining globally for at least 40 years. And even as you see, since 1990, the number of weather stations of sufficient quality for inclusion in global climate analyses has been declining, whatever continent that you are looking at. And there are a variety of reasons for that, but on the other hand, technological barriers to designing and building your own environmental monitoring have been falling over that time. So 3D printing, low-cost microprocessors, etc., mean that we don't have to rely on expensive commercial products that are expensive to buy and expensive to service. We can build our own and achieve similar levels of quality. FreeStation is an open source project that provides designs for low-cost environmental sensing for education and research. You can build things at around 3% of the parts cost of equivalent commercial loggers, which either means you can save a lot of money or means you can have many more data loggers, environmental monitoring stations, and thus do more with them. And since geography is important, the world is very variable, it's great in research as well as in teaching to be able to have more instrumentation. Our second generation of FreeStations is based on web-connected technology, Internet of Things, and that allows for all sorts of interesting interventions such as early warning systems, nowcasting, or integration with weather forecasts, as you'll see later. There are many low-cost sensing projects out there. FreeStation is not the only one. FreeStation is a relatively mature project, and it's designed for stations to be built by geography students, so they're easy to build and you don't need knowledge of electronics. So we build a variety of instruments, all of which are good enough for the job. Designed, they are with consumer off-the-shelf and thus cheap components. All parts are replaceable on our stations, and all stations can be reconfigured to different types of stations. So you can build a weather station and then use the components later for other types of monitoring. They're easy to build, easy to ship, and easy to install. They're robust, they last a long time in harsh environments, and we've tested them in some very harsh ones. As I said, they're network enabled where that's suitable, and the designs are open source. We also have a web interface where the data goes that makes it easy to visualize, manage, and analyze the data that you produce. Low cost doesn't have to mean low accuracy, precision, or quality. Low cost actually means that we're using non-specialist consumer mass-produced parts and do-it-yourself or volunteer labor. And since mass-produced parts are cheap, then that's where our low cost comes from. We're not relying on specialist components that are only used on weather stations. Here are some examples for you. This is an accuracy assessment of different types of sensors compared with commercial weather stations. We're within 0.5 degree Celsius of temperature. We're within 2 or 6% of humidity. Our river level stations can be within 1 centimeter depth for very cheap sensors on large rivers, 1 millimeter depth for slightly more expensive sensors on smaller rivers. There is reproducibility between our stations. In other words, the sensors give the same results across stations. So why would you build a sensor? You can build them to use in the field, i.e. In a research site, in your own garden. If your garden is your research site, if you're a dissertation student, for example, or doing an EPQ, or indeed in your home, if that's the space where you're doing research. You build a sensor because it can collect much more data than you can do by hand, because it can collect data when you're not there and do so very frequently over time, which you don't want to do manually. It can provide, through measurement, the environmental context for a range of studies: biological, geomorphological, hydrological, agricultural, and even social studies. And sensors help you understand the spatial variability between places, i.e. geography, also the temporal variability over time, including the diurnal cycle, the seasonal cycle, etc., etc. And sensors allow you to do experiments in the field, in the garden, in the home, where you are manipulating the environment and trying to understand the consequences of that. Why would you build your own sensor? Well, as we mentioned, it's much cheaper. You can use many more sensors. You can support local monitoring capacity in a cheap way, and you can empower communities with the evidence to influence regulation or policy. We've built around 500 FreeStations, and we've deployed them around the world, as you see from this list and the map in the background, really doing a wide range of work. At some of these sites, we have 50 odd FreeStations of different types. And so we have a dense network of monitoring, in some cases, the densest network of anywhere in the world. Over time, of course, the data that we've been collecting from these stations has been growing as we built them. And this year so far, we've already recorded 22 million readings from these stations. Where we think such technology is useful in education is in a wide variety of areas. We, of course, use FreeStations in our own education work at university level. We use them both to support field measurement by students during field trips. We use them in the classroom, including to have the students building sensors as part of their dissertations and as part of their practical work. And we supply students with stations also for their dissertation work. In school education, we think FreeStation type technology can also support field trips, either at field stations or indeed day trips out from the school. We think they can support dissertation, NEA, EPQ type work, if you have a stock of data loggers that can facilitate projects in either long-term monitoring over a summer, intensive field days of sensing, where the student might be logging data every minute at multiple locations and comparing them, mapping, because we have sensors that can be carried walking or cycling, so-called walkables, with GPS enabled to enable the data to come also in map form, and of course experimental work in the lab or in the field where you manipulate the environment for an EPQ in some way, for example, excluding rainfall or increasing temperature, and look at the impacts. We have a whole series of ideas for dissertation topics, more than 120 of these based on FreeStation instruments. There are also, I think, links with the curriculum We're working with teachers at the moment to develop multi-lesson enrichment activity. Some of that you'll hear about in a minute, but also lesson snippets of just a few minutes where monitoring as an activity, you cannot manage the environment if you don't understand it. You can't understand it if you don't measure it. So monitoring is fundamental. Monitoring activity is relevant in a wide set of areas of the curriculum, including, for example, weather, climate, place, geographical skills, fieldwork, and water. Research, of course, in academia is sometimes a rather complicated affair, but our students always do much more simple research because the resources and the time is much less. With sensors to view different elements of the world, EPQs or NEAs can take place in the home or the garden and still be original and exciting because you're viewing the world in a different way through a variety of sensors, not just with your eyes. You first, of course, consider what variable you might measure, such as air temperature. You decide on a question, and for each variable, we have in our 120 questions document, we have at least 10 specific questions that you can ask of that variable in a short period of time. For example, how does soil moisture react to rainfall events, and how does this differ for soil moisture probes at different depths? For a temperature sensor, you could ask, what is the gradient of temperature and humidity from the interior of a room to near the window of the classroom, and how does this differ for north and south facing rooms? So you decide on a question. That question might be about variation over space, variation over different settings of control, sunlight versus shade, for example, variation over time, or comparison of one variable with another, for example, temperature in relation to solar radiation, sunshine. Or the question might be a comparison with a human driver, such as road traffic, effects on pollution, heating, effects on thermal environment in the home. So once you've decided on a question, of course, you need to build the appropriate FreeStation, and we have a wide variety of open source designs that students can build with support from teachers, particularly in design and technology classes. Of course, you need to test what you built to make sure that it works properly. You then deploy. If you're leaving the stations unattended, you must get permission. You collect the data, upload it, and analyze it, of course, to answer the question. So there's a link here to our EduStation website, which is a subset of our FreeStation project focused on education, where you can get these questions and the kinds of setup that you might need to answer them. What can you build? Well, of course, weather stations can be built that measure things like rain, fog, wind-driven rain, air temperature, humidity, solar radiation, even photosynthetically active radiation, that's part of the electromagnetic spectrum of sunlight that powers plants, wind speed and direction. You can measure soil moisture with data logging, water quality, air quality, rivers, and a wide variety of other kinds of variables. We have two generations of FreeStations. We won't really discuss generation one. They're a bit more difficult to use. They're based on a microprocessor called Arduino. They write data to an SD card like you would have in your phone, and you read data by opening up the logger, taking out the SD card and reading it on a computer. Generation 2 are based on an Internet of Things set of sensors, microprocessors rather, called particles, photons and electrons. The photons are Wi-Fi connected, but don't have to connect at all to Wi-Fi if it's not available. They can also write to SD card. The electrons use the GSM telephone network. So the Wi-Fi's we call locals because we go to those stations with a phone, and the mobile phone reads the data off the station. The GSM sensors we call lives because they send the data directly to the internet every hour, whether we are there or not. So here's a soil moisture station, here's a river level station, here's a weather station and another one here. Here are a few other pictures of various stations that can be built and their cost, all the way from the classroom demo that we're going to discuss today, to water quality, to river level, to outdoor air pollution, through to rainfall and soil moisture and weather. And what you saw here was our scanning LiDAR, which measures profiles across channels or hill slopes. Costs about £160 to build that, and is probably the most sophisticated form of equipment. So I'm going to hand over now to Lady Eleanor Holler's school, where Andy Britton and his students are going to take us through their experience of building a FreeStation weather station. Thanks, Andy.
Hi, I'm here. Can you hear me? I can't see myself. Okay, assuming
We can hear you, Andy. You're quite echoey, though.
yes, I think I will. What do I do? Turn this. If I mute myself, no. What
It's
can
much
I
better
do?
now.
Is it?
Yes.
Is that better?
Yeah.
Okay, wonderful. Well, my students, towards as we approached the pandemic, I can hear an echo again. Right. As we approached the pandemic, we picked up this project, and actually it took ages to collect the materials together. But essentially, the students were utterly incredible and managed to move through and develop all of the equipment necessary, collect it from all over the world, and piece it together to produce their FreeStation. And we've just had it installed in the school grounds. It's been utterly amazing. But I'm going to hand over to my students who should be there. I'm in a different location, but if you could take over, I will mute myself. I'll let you go.
Our video doesn't seem to be working, but we hope you
can you hear us clearly?
We can hear you.
Okay, that's we're from Lady Eleanor Hollis, and we're in year 10. We installed our FreeStation outside a few weeks ago after starting the project a year ago, although this did include the second COVID lockdown, so it should be quicker now. I think we all found it enjoyable to work in a team, and it wasn't only fun, but it was also educational, because before I only had a vague idea about how machines like this work, but this project has given me a hands-on experience.
Yeah, it's also helped us to understand how weather patterns change as we've had to do our own bit of research.
I think that we have managed to make many projects from this one, as we have started to...
So we're hoping that with all this design technology skills, we'll be able to put them forward in the future, as well as this weather station skills have been vastly helpful to us, because we're picking up analysing statistics, which we're gaining from the weather station, and hopefully this is going to help the environment in a positive way.
Other skills that we had to learn and improve on were like soldering and building the actual weather station required construction techniques, and we also had to learn to be really careful and be able to spot where there might have been a mistake in our soldering.
I think working in a team was very useful, as if one of us didn't know something, the others could help, and we learned lots of teamwork skills and our best areas of expertise in our group.
So we would recommend working in a team for this project. Some of the challenges we faced were that when we ordered parts, we might have ordered the wrong ones, or because of COVID especially, parts took at least 2 to 3 weeks to reach us. And also some of these parts were faulty, so we had to reorder them, which sometimes delayed the project.
Yeah. Due to those challenges, we have a few recommendations. One of them being that if you are going to do it, make sure you order the equipment beforehand, because due to the halt in production, it did take a while to come to us.
We also think that checking the sensors work before installing it outside is quite important. So it saves a lot of time.
But also, while facing these challenges, we still persevered, and that's how we ended up with our working weather station now. So we just have to keep getting through it.
Our aim of the project is to see how government mitigation policies are effective.
How they affect our climate patterns and weather patterns.
And we can analyse all of our data to find these conclusions, and it's very useful for separate projects. And we hope that future generations will also learn and use this weather station to make their own projects.
Also, Professor Mark Mulligan has been really helpful for us through this entire process, so we owe you a big thank you.
Thank you very much.
Could I add something to that? You turn off your audio for a second. Right. Yeah. One thing I will stress is that what it brought out in the girls was just amazing. It brought out all the best possible skills and qualities. And I think if you're going to follow this project, I think you'll see the same thing. And the delight that takes place when you actually manage to communicate with your sensors and are aware that they're collecting the data and that's what these students have produced. It's just phenomenal. And we're on to the next level now, where we're taking the data and collecting it. It starts to feel a bit like a construction project, but it doesn't end. And the sort of the future aspect of it, putting this into the grounds and seeing this as a generational thing that students will be collecting data, repairing and moving forward is also quite inspiring. So with that, we'll end. Thank you very much, Mark.
Thank you very much, Andy, and students, for that really good overview of some of the challenges and the problems, but also that you eventually got there. I think you've done a brilliant job. You even improved on the design, and we'll be bringing those improvements into the design for others. So that's been a really positive experience working with you. And as I understand it, you're heading off to the Royal Society in a few weeks and you'll take your weather station with you to the summer event there, which I think will be really, really a positive thing. So thanks for that. I'm going to now reshare my screen and we'll move forward to Sophia. Just tell me when you want me to change slides.
Okay, thank you. Can you hear me? Okay,
Yeah.
so I'm just going to give a few examples of how we've used FreeStations. I work for an environmental research consultancy called AmbioTEK, and we've used these designs in our work for environmental monitoring and hazard monitoring, and found them very useful because within a it's good to have low-cost solutions, because within a tight budget you can make multiples and therefore get a clear view of the environment and what's happening in each of these areas. So I'm going to give 3 examples here. First of all, looking at noise pollution. This might be interesting for teachers from schools that might be located near a noisy road. In here we've got 3 noise pollution sensors. At the bottom there you can see the A127 on the map, and 3 sensors at different distances from the road, and the results data on the left with the sensor nearest the road in yellow. And very interesting results. And it might be interesting to apply this sort of project in schools, because the WHO guidelines for community noise recommend less than 35 decibels in classrooms to allow good teaching and learning conditions. I mean, here it's not within a classroom, it's in the open air, it's in farmland, and it's the one that's close to the road is very close to the road. But as you can see, you could adapt this experimental setup to be something quite interesting. Next slide, please. This is to do with air pollution. The school street scheme is implements a traffic ban directly outside schools during peak hours when the children are dropped off and picked up. And it makes the roads around schools safer for children, safer. But our question was, is school streets actually better for our health as well as an additional benefit? So we put up air quality sensors around the school, logging every minute for 1 day, very intensive monitoring. We strapped them to posts with temporary cable ties. You can see we got council permission for these, as it was just for 1 day. That was fine, and we put some inside the school street zone and then further down the road outside the school street zone where the traffic was normal and measured throughout the day to look at whether the air quality was affected. In addition, you can use fixed air quality sensors that are installed at a safe height for a number of weeks. We did that with council permission, but note that if you're going to use this with students, it has to be at a certain height so that it's away from thieves and vandals, of course, and therefore working at height has health and safety implications. So there's some things to think about there. And these sensors measured particulates in the air and gases too, nitrogen dioxide, nitric oxide, and ozone. And as you can see some of the results there, you can see a very clear decline in particulate matter throughout the morning there, and you can see the effect of school street zones. So it has some very interesting results. Okay, thanks. Next slide, please. And finally, another air quality one. What's the impact of the research question could be, what's the impact of cooking on indoor air quality? Because the air we breathe in kitchens can have pollutant levels many times higher than the outdoor environment, particularly compared to city centres and along busy roads. The levels are comparable. So we monitored particulate matter at 2.5 microns, which are inhalable particles or droplets in the air. They're very small, that can travel into and deposit on the surface of the deeper parts of the lungs. So these are sort of more dangerous particles, and so we monitored them. And the EU Air Quality Directive allows an annual average of only 20. And some of the results here of a sensor in a kitchen shows many times more than that. You can see this is, each of those bumps is for the day. So that's a whole week of data. And you can almost see every sausage and every burger being fried. This is every minute in a kitchen for a week. This is in a kitchen that's commercial kitchen, and it has an extractor fan. So you would have thought it was quite surprisingly high. And in addition, you can also compare this data with our fixed outdoor sensors to give a sense of reality of, how high is this data compared to the streets that around the school that we walk. So that's an interesting idea for a project. Okay, thank you. Next slide.
Okay, over to Arnout.
Thank you, Mark. So my name is Arnout Soesbergan. I'm a researcher at King's College London, and this is another example of how we're using FreeStations in our research. This is about leaky log dams with a research question of trying to find out if leaky log dams are actually capable of slowing down the flow of water in streams and rivers. So leaky log dams, as you can see on the picture in the center, are a form of natural flood management. They're used to hold back small volumes of water. Picture on the right there is the same log dam. This is a site in Essex that we're studying during a high rainfall and flood event. And so you can see it's completely submerged. And what we're trying to do here is to monitor upstream and downstream of the leaky log dam to see how well this dam is capable of holding back water. And so if we look at the graphs, you can see on the left, in the gray bars is a rainfall event, and the blue line is the distance. We're monitoring the distance to the water, so the water level. There's initially a lag time after the rainfall event, but then we can see the water level go up. This is on the upstream, the water that is kept behind the dam, and then slowly it goes down again. And then if we compare that with the downstream sensor, that's the graph at the bottom there, where we can look at the rate of change between the two sites, or between the two monitoring stations. We can see that it's going faster in the upstream during the rising limb event, and that it's pretty much the same after. And so this kind of information can help us to see how well these dams are functioning, how much water they are capable of holding back in the landscape. And I should also mention that at this particular site, we are monitoring lots of other interventions as well. So we have sensors further downstream. As I mentioned, we're also monitoring the weather there, the rainfall. So we have the weather station on the bottom right there. You can see where we're monitoring the local weather conditions. And we're also monitoring throughout this relatively small catchment as an experimental site. Back to you, Mark.
Okay, thanks, Arnout. If anyone has questions for the school or for Sophia or Arnout, just use the Q&A function and we'll get those answered for you. So you've seen a wide variety of different applications. As I said, these stations are designed to be built by students. Here are some of our students building FreeStations. This was a team of girls a couple of years ago who got some funding from the Royal Geographical Society to head out to the cloud forests of Peru to help with an experiment that we have ongoing there. They called themselves Girls of Cloud. And as you can see, they are soldering, they are bending metal to create the enclosures for FreeStations, and they are cutting tubing, and they are filing off the sharp bits. And so, you know, they're just following the instructions and built a whole bunch of around 6 weather stations that they took out and have been deployed and in use at that site since. The reason that's possible is, as I mentioned at the beginning, you know, technology has really improved. 20 years ago, when we started monitoring the environment, when I started monitoring the environment, we had to work with data loggers like this, and they were good at the time, and they still are good. But you know, if we're talking about education and research, these are still very expensive. A data logger this size now shrinks to a particle photon around this size. And the particle photon has most of the same functionality, in fact, more than a logger this size, and it costs about £19 instead of 3,000. But of course, you know, the challenge with the particle photon is that you have to have a design of a printed circuit board, and you have to have code that runs it, and you have to have all the design for all the electronics that attaches. Well, that's the bit that we've done, which means that, you know, makes it possible for you to do the kind of logging that was formerly done with this, with something much, much cheaper. And FreeStation designs are well tested since we've built very many of them. The designs have evolved and improved. They're now widely deployed. They're low cost, open source, easily portable. And if you combine you know, version 1, generation 1 and generation 2, at the point I did this slide, it was 300. We've now done about 500 stations. All components are sourced from eBay. Some come from China, and that creates the delays that we've been talking about. Sometimes the parts take 3 weeks to arrive. You can often buy them in the UK as well, but they're usually much more expensive here. So if you're buying a lot, you get them from China through eBay. If you're not, you get them from the UK through eBay. What makes this all possible is the FreeStation printed circuit board, this thing here. That's the bit of glue that we have designed that helps you to put all the different pieces together of the components to create a data logger, whether it's in the classroom or in the field, that does the job. And I'm now going to move into sort of demo mode and stop sharing and show you in practical terms what we're talking about here. So I'm hoping that you can now see what I can see, which is the table. And I'm going to show you some of these components. So I just need to put that in gallery view. Like that. Okay, and so as I mentioned, this is the FreeStation printed circuit board. This is the only thing that you don't buy on eBay. It costs around $13 for three. Sorry, for one, but you can only buy them in packs of 3 from the US with free postage, although it takes 3 weeks. And as I said, this is the foundation or the glue, because what it allows you to do by adding headers, and a header looks like this, by adding headers onto this printed circuit board in the right place. That's a header. Okay, you solder it on the back like that, where the pins are, and the header allows you to plug in components like the particle photon there in the right place. Okay, so you have a series of things that you pop into this printed circuit board. So we have sockets. We use Ethernet sockets to connect sensors, or phone sockets, because they're easy, they're practical, and the cables are cheap and good. So I've just plugged in an Ethernet socket, which is that one there. I'll plug in a phone socket, and then of course we have to solder these sockets. We have a power outlet, so I just plug that in there. That's the barrel jack power outlet. And then we have a series of switches that are used to control the timing of the device. So I pop that in. Now, of course, after popping these all in, I need to solder them, but I'm not going to do that now. And then what we end up with is a circuit board with the headers and sockets soldered on. That's what that looks like. You can see those headers and sockets soldered on there. And then, of course, when we put the components in, we end up with something like this. Okay, so this is a classroom demo, which is our simplest FreeStation and cheapest. This costs £30 or $35 to build. It's designed for use in the classroom, so it has no enclosure or anything like that. It has the photon, the particle photon there. It has the switches. It doesn't have an SD card because it writes directly to the internet. It doesn't have a real-time clock because it gets that from the internet, gets the time from the internet, and it has a series of batteries. So that's what makes it very cheap and very simple to build, because you really only have to add a couple of headers, a transistor, the switches, and the sockets, and you're done. You then, of course, add a sensor, and what we've added onto this is a sensor called the BME 280, which is a temperature, humidity, and air pressure sensor. And like all of our sensors, it is added via a small printed circuit board that you also need to buy. It costs $3. This is called the RJ45 board, because it connects a sensor to a cable called an RJ45, an Ethernet cable. And so we can easily unplug that and plug it in. We can easily remove the sensor if it's faulty or becomes faulty and replace it, as we can for any other part on this device. And this device has been recording for the last couple of hours every minute, and it's sending that information to the internet, and we'll take a look at it in a bit. So that's, if you like, the basis of FreeStations in terms of their brains, the data logger itself, and sensors to connect. I'll show you another few things here. I won't show you a full weather station, but because I don't have room underneath the camera here, but this is the latest version of our temperature, humidity, air pressure, solar radiation design. It uses, as you see, plant pot bases to create a Stevenson screen. It has a solar radiation sensor, cheap solar radiation sensor on top, and it has the temperature sensor at the bottom, protected from heating by the sun. This would normally cost about £600. We can build this for about 16. Right. So, and that is, of course, an important component of a weather station, to be able to measure those variables. This is our FreeStation rain gauge design, and the girls at LEHS produced this exactly for their station. It has a tipping bucket rain gauge in, a very cheap one. You can hear it tipping there. But the design of the tipping bucket as a rain gauge is not very good. So we enclose it in a box like this, and we put a proper funnel on it with a spirit level, and we protect it from insects and other things with mesh underneath, but it still drains, and that works very well. Gives us instantaneous rates of rainfall as well as accumulating rainfall at the logging interval of the sensor. So I mentioned this sensor connects every minute, and it's just doing that. Hence, you may be able to see the lights on the sensor that tell you what it's doing as it sends data to the internet in different colors. Right, flashing green, connecting, breathing green, connected, and then yellow sends the data, etc., etc. So what else do we have here? We have a range of other sensors. So this one here is our river level sensor. This is based on a parking sensor for a car. They cost about £8. Very good at detecting the distance, as Arnout showed you, between a bridge, for example, or installation of this on a pole and the river surface, so that you can measure river heights in that way. Like all our sensors, we put, if they're being put outside, we put them in waterproof enclosures. Usually they are like this, with again either a telephone cable or an Ethernet cable to connect the sensor into the main station. The challenge of building sensors is keeping the environment out of the sensor and out of the data logger. So most of our data loggers, we don't open the boxes at all for the years that they are in the field, because we go up to them with a mobile phone, we transfer the data that way. We don't open the boxes, because once the humid environment gets in, then that's not very good for your electronics. Okay, what else do we have here? So we have a series of stations that we build for student fieldwork. What we tend to do with those is we put them in transparent boxes, or at least boxes with transparent lids, so that we can, explain what is in here. It's not a black box. You can see the data logger, the switches, the battery, the screen. We do tend to put a screen on them so that you can read the data, but also these send data to the internet when you return home from the field. This particular one is a soil moisture sensor that we use in fieldwork. We get students looking at spatial patterns of soil moisture, for example, downhill slopes or or between vegetated and non-vegetated areas, between grasslands and forests, across forest edges, that sort of thing. These are, you know, relatively easy to build because you don't need all of the screening that's required to leave a logger in the field. So that one is soil moisture. This one here is same system, but connected to a different sensor, and we have a wide variety of these. Obviously, I'm not going to show you them all, but I'm just showing you a few. We usually take about 20 different ones on a field trip with about the same number of students or groups of 2. This is an albedometer. It measures incoming solar radiation and reflected solar radiation. It's carried like that. And again, we use this to look at the differences created in microclimate from different surfaces, for example, paving versus grass land. These can obviously be used in the school grounds as well as on a field trip. And indeed, we use them also for demonstration purposes on the premises. So that's those. We then have a couple of other sensors here. These are GPS enabled sensors. Again, we use them in student field work. They have a GPS chip on top here that connects into the FreeStation data logger. This particular one is measuring sound pollution. As Sophia mentioned earlier on, this is a noise pollution sensor that takes measurements in decibels. The students carry these around or cycle them around streets or gradients, and this records the location as well as the sound intensity, and automatically when you get back, you switch them on and off again, off and on again, upload the data, and then you go to the link. The link is always the number of the station, 316 in this case, and it provides you with a map color-coded of your noise pollution and allows you to download the data. So I'm sure you can think of practical ideas for using that. And then this one here is exactly the same, GPS enabled data logging device, but this one does air pollution, in particular particulates. So again, as Sophia mentioned, this is the air. There's a fan in there that pulls in the air in and out, and a small low cost, I think this one is £8, particulate sensor that works out the PM 2.5, PM 10 and PM 1 in the air that you are walking or cycling through. So again, lots of potential possibilities for student work with those. And then finally, I will show you what our sort of standard data logger station looks like. Of course, in this case, we have the station, the logger itself in this box, well protected from the environment, sealed completely. And the only thing that comes out of this box are the cables to the solar panel, the cables to the sensors, and a small switch to reset the station. And so if we're deploying for a long period in the field, wherever, whatever environment we're talking about, this is the setup we have. We have the sensors on the side. So in this case, this is monitoring particulate pollution at the side, temperature, humidity, air pressure underneath. And the air pressure data is needed to interpret the particulate data. It's all the electronics are in these boxes. And then the boxes are shielded by aluminium to keep the sun off them, because heat and electronics doesn't go well. We then have a sort of lid on top that keeps the sun off the box, and of course a solar panel, a large solar panel in this case, because the components, the sensors require a fair bit of energy. And this can be left in the field for years on end. It will record data every 10 minutes. We visit the station with a device that we call the FreeStation relay, which without mobile phone signal transfers the data. When you press reset on this box, transfers the data from this box through your phone to the relay, and then you take the relay away and upload the data. This station you can build for about 160 pounds, a bit less, if you build multiple of them. So that's a whole bunch of examples of the kinds of things that can be done. So I'll start sharing screen again now. We'll go back to the final part of the presentation, hoping that we're leaving plenty of time at the end for questions or an early finish. So this is what I just showed you. You know, the components are the particle photon. There's a little switch on there. There's the timing switches. There's a transistor. These are the RJ45 sockets. These are the telephone sockets that are called RJ11 sockets, the power cable, and the socket for the power. The classroom demo, that's all it needs, right? It doesn't need anything else. But if you're building a weather station that you're going to deploy in the school grounds or anywhere else, it also needs a clock, because if it's not connecting to the internet, it needs to know the time. And it also needs an SD card because it needs to store the data locally and then send it when you reset it. Whereas the classroom demo just connects every minute, as I showed you, and just pulls that data over to the internet. So I showed you blank and populated printed circuit boards. I showed you the components of an automatic weather station. I showed you a stage sensor made out of a car parking sensor, a pollution station, and then a bunch of our teaching loggers, soil moisture, albedo, and GPS. The classroom demo logger that I showed you, flashing away, collecting data, well, that's been on, as I mentioned, for a little while. And this is the data that it's sending to the internet. I had it in my workshop at the top of the garden. Looking at the temperature, it was relatively cool in there. I took it outside to the house, as I brought it down to the house, and it's much colder outside. Put it in the kitchen where it's nice and warm, and temperature increased. And then I brought it in next to me, which is a little bit cooler. And as you see, it's been getting slightly cooler over time with some hot air that I was obviously producing as we began the presentation. So that's how temperature is operated. And this is how humidity has responded as well. And of course, if we look at air pressure, then not a great deal has happened there. You know, we're only talking about 1 millibar difference, but certainly as I brought it into the house, it's slightly higher pressure in here than it is outside, but not a lot of difference at all. So, you know, that's the kind of thing that you can do with these. You can come up with all sorts of ideas for using them. If you want to go building, then I should say we don't build stations for anyone else. That's not, as an academic institution, that's not what we do. We build the designs, we open the designs, you build. Everything is documented on the building, installing, and using, as well as data and tools and live data. If you have questions on the instructions, the documents are all Google Docs. They are commentable, and we will improve the instructions with your comments. We are about to produce a load of videos because at the moment the instructions are based on text and photos, and sometimes that's not entirely clear. So we will produce some videos starting with this one that help you to understand how to get this done most efficiently. I think, you know, what the girl said is absolutely true. You know, just be aware of the time it takes for stuff to arrive. be aware of making mistakes, of faulty components, and so on, and just test as you go. So if you're building your FreeStation, you go to freestation.org building. You probably start with building the sensor in its enclosure. You then put the microcontroller on the printed circuit board with the SD card and anything else you need. You then need to upload the firmware, which is the software that the device uses to control, so that we can control what it does. And when you buy a particle photon, it's blank. It doesn't have any firmware for data logging. So you have to upload the firmware that we have used, and that does everything that we have shown. Obviously, you add the batteries. If you're putting the thing outside, you need a housing. And the instructions are, as I said, text like this, and images that interact with the text. And we've had a number of people go through and build successfully without a great deal of solid help from us, just a few sort of questions and answers as you go. And in the case of the girls at LEHS, they switched it on a couple of weeks ago and it worked first time, which was very impressive. What do you need? You don't need much in the way of tools. They're designed not to require much. You need a bench, workshop, shed, kitchen table, or of course, a lab in a school. You need a few tools, and some of which are relatively specialist, such as a hole punch here. You need a soldering iron, steady hands, safety gloves, protective glasses. You need to be able to follow the instructions and to problem solve. In other words, if something goes wrong, it's not a problem necessarily with the design, because we have hundreds of these working. It's something with the implementation of it. And all our stations also have problems when we don't quite build them right, or when they get damaged in the field, or when they just wear out over time. And it's just a case of using a electronic kit such as a multimeter here to check that the electricity is getting where it should be and the voltages are about right, and take components out one by one, and when your station starts working, you know which component was the problematic one. There's no magic in electronics. It's all, as I'm sure Andy would tell us, about physics. So you need time to build these things, and students need time to build these things. It's not something that can be done overnight, but once you've got them, of course, then you've got them for years and years and years. So just to provide a bit more detail on the process of building the classroom demo, which is the simplest data logger, there are, as I sort of indicated on the previous slide, a few steps. The first one is to build the thing. You then need to upload or flash the firmware, which is the software that the particle uses. You then need to switch the thing on, connecting it to power, and then it will register to the FreeStation website, which provide you with a number, the so-called F number or L number, which you can use to get to your data. So the first part of that is to source the components. We have a bill of materials, which is a spreadsheet that looks like this. And the bill of materials lists for the classroom demo everything that you need to buy. And it doesn't provide a link to eBay, because the links always change. It provides you with a piece of text, a search term that you copy and paste into eBay, right? And so long as the component looks like the picture, then you'll be fine. The prices may have gone up a little bit, of course, and because we're in an era of inflation, but they won't be much different. So that's the first step, is to go through the bill of materials and to source your components. The only one that's not from eBay is the PCB itself. And then once you've got the PCB, you are adding those components to the PCB in the way that I indicated earlier. That requires soldering. Soldering is the only skill you need. I'm not going to play this video now, but you'll get these slides and you can view this video later. It explains to you how to solder, and it's one of those things that you know, once you've done it a few times, it's easy, but when you first try, it's difficult. And of course, soldering is important because you need a good connection between the different components. The key thing to avoid is bridging when your solder connects two pins together. That's obviously a bad thing, and you need to remove excess solder if you end up with that. So that's a good YouTube video, just a couple of minutes long, on how to solder. So once you've put together your components, you need to put together the sensor that you're going to attach. In the basic version of the classroom demo, the sensor we use is the BME 280 temperature, humidity, air pressure. You attach it to a small printed circuit board like this, exactly in this way. So that's the sensor. It pops in to this header here, and then the cable to the main logger goes in here. All of our devices are structured in this way, and it means that everything is interchangeable, and everything is removable, repairable, and reconfigurable. Once you've got the sensor together, you attach the sensor with an Ethernet cable. We use flat ones because they're easier to manage, between the sensor and the main logger on its board here. You add the particle photon, you just push it into the headers that you've soldered. You attach the battery pack. In the classroom demo, we use simple rechargeable nickel metal hydride batteries because they're very safe. In the field, we usually use lithium batteries, but of course, you know, you short circuit those and you have problems. So these are much safer, and then you're done. And so the next step then is you go to the build document and you download the firmware file. This is just a binary file that is the software that runs on the logger. With that file, you need to install the Particle command line interface, it's called. It's a piece of software from Particle that you install on your computer, and it looks like this. When you've installed that, you put the Particle into something called device firmware update mode, which just involves pressing a couple of the pins in a particular order, the buttons in a particular order, until you get a yellow flashing light on the Particle. It's then programmable by plugging in a micro USB cable into the computer that has this software, into the Particle, and issuing this command, where name of binary here is the name of the file that you've downloaded. That will upload that firmware to the Particle, and you know that has worked when the Particle issues these colors in order: red, green, blue, yellow, cyan, fuchsia, because that is the signal that the FreeStation software is running. And so whenever you press reset on the FreeStation or you update the FreeStation, it starts with those colors and you know it's running the FreeStation firmware. So you see we have firmware for a variety of different sensors. You have to have different firmware for different sensors. So depending on what classroom demo you're interested in running, whether it's, you know, a rain gauge and you then put it in a box outside, temperature, humidity, river distance, etc., you have different firmware there. The next step is to switch on. And the classroom demo, as I said, doesn't have an SD card. It connects every minute or every 10 minutes or every hour or continuously, either to your school Wi-Fi or more easily to your phone. So the data that you just saw was just the classroom demo I have sitting in here, tethering to my phone and sending the data that way. My phone is connected to my Wi-Fi, so it's not costing me any data costs. It's just sending data from the FreeStation to my phone and from my phone through my Wi-Fi to the internet. In order to do that, the FreeStation is going to look for a Wi-Fi hotspot name called FreeStation, which must have this password. Now, you will only change your mobile hotspot name temporarily to this when you're doing demonstrations or classes with the device. Otherwise, you would use a school Wi-Fi or something like that. Once you've set up hotspot, you plug in the battery, and the FreeStation will cycle through these colors. First of all, the red, green, blue, yellow, cyan, fuchsia that says, okay, I'm a FreeStation. Then it starts blinking green as it starts connecting. If it goes red, it couldn't connect. And then other colors tell you what it's doing. Once the FreeStation has connected, it will be assigned a FreeStation ID number. And you can get that ID number in one of two ways. Either you have to follow instructions here to get the particle ID from the particle device, or the easier way is you just click here, which tells you the last registered FreeStation. And if you've just switched on your FreeStation for the first time, this will be the one that you have registered. And indeed, the last registered one was the LEHS one, 339, and it'll take you also to what we call the configuration page for that station. And the configuration page for that station, it basically tells you what's happening. So in the bottom right here, it tells you with the most recent at the top, the last events. So on the 6th of the 5th, data was sent from this station. The time was retrieved from the server. The configuration was sent to the server. Data was sent. And then before that, other things happens. It tells you any troubleshooting information, right? We have a loose connection on the temperature sensor on this station, and so it says failed to boot sensor, and so we have values of 0. So that's being fixed now, and a couple of other things that are just useful information. It tells you, the setup of the station, and it gives you the latest piece of data that was sent. So that's how you find out what your ID is. And then finally, you make sure that your switches are set for the recording interval that you want. If you want to log it every minute, then switch number 2, the one that's labeled number 2 here, is on, and all the others are off. And that's it. Of course, the classroom demo and any FreeStation can be attached to a wide variety of sensors. These are all the kinds of low-cost sensors that can be bought, and the kinds of things that can be measured. Most of which are, of course, very relevant to geography, but some of which are relevant to other disciplines, physics, biology, etc. Our smart system, the sort of web-based interface that you access your data from, makes it easy to both visualize and analyze and download data. So if you have a FreeStation active, then it provides you with information like this. So this one is our Spains Hall weather station, which, as you can see, was deployed in 2019 and is still collecting data. And this station, I'm looking at the data now live. This is forecast data as well as measured data. So now is the rainfall that's happening in Spains Hall recently and today. But because the weather station sends its data to the internet, we have connected it to, as any FreeStation can be, using this system, to a forecasting model. And so we have forecasts that there will be more rainfall over tonight and tomorrow, and then the temperature will gradually increase over the next few days. We can plot the data in a variety of ways. We can look at, the whole month of data. We can look at the whole year of data, and so on and so forth. We can look at different variables. Instead of rainfall, we could look at solar radiation. We can plot these as a scatter graph if we wanted to, all sorts of things. So that's sort of web-based system that facilitates the use of data both in research and educational settings. It means you can easily get to it. Oops, sorry, I didn't mean to do that. I meant to do that. And so here's another example. This is a data set from a station in Colombia, at one of our research sites. And again, you know, we can look at perhaps the whole year of data. This was from 2019, and all this data is stored for a long period. And let's compare, I don't know, temperature and solar radiation. Obviously, temperature has a strong diurnal pattern as well as an annual pattern, not much of one in Colombia because we're basically on the equator, about 10 degrees north. And it's also related, of course, with solar radiation. So if we plot as a scatter instead of a time series, temperature and solar radiation, then we can see that I should have these the other way around really, but as of course solar radiation increases, temperature increases, it's non-linear, and there's a lot of scatter because of course the scatter is determined by other things than solar radiation, like where the wind is coming from and so on and so forth, air masses, etc. If we want to download that data, then of course we can. So let's not download a huge amount of it just because of my connection here, but let's download the last week's worth of data that was collected. We can just download the variables that we're viewing at, or we can download all of the variables either as a text file like this and copy it into a spreadsheet or whatever we want. So that's the smart system, and of course that's invaluable for the work that we do, because you know, with hundreds of these stations we have to be able to manage the data and manage the stations and not spend a lot of time messing about in spreadsheets. We don't do anything in spreadsheets. It's all done online in the system, including various types of analyses. It's not just about time series, it's also about maps. So you know, we can look at a range of stations in map form as well, or we can produce maps for a single station if it's GPS enabled. So here what we will be looking at is a range of stations again in Colombia, like the one that we just saw. These stations we've just added the location of the stations to the station configuration, this is the location of the stations, and the color here indicates the temperature varying between 14 and 24 degrees at the same time, right? So this is an analysis of spatial variation between a series of stations. FreeStation also has all its data open access, so any data that you produce will also be open access. And this means that you can, in schoolwork, use any of this data with your students. Just find the station on the FreeStation map of stations, and whatever is of interest you can either visualize, play with, download. And of course it also means that as more schools produce stations, then there will be a network of these within schools. And indeed we have a project in London that is focused particularly on building a network of weather stations across London schools. So just to finish off, a few cautions. You know, you really can't just put a monitoring instrument out in the environment, either in a rural or particularly in an urban environment. Get landowner permission and make sure you label the device so that people know what it is, including who to contact. If you're working in cities, it's really important to do that and to be very careful of where these are deployed. We once had a phone call from the bomb squad because a student had put a self-build pollution monitoring station on top of a bus stop, which, you know, wasn't very sensible. These things, you know, look suspicious, and so you've got to be careful where you put them, and you've always got to get permission. When you're soldering, use lead-free solder in well-ventilated conditions and wear eye protection. And take care to store batteries properly. They are the only dangerous thing in this, other than saws and solder. And of course, don't short circuit batteries, especially lithium ones. So thank you very much. If there are questions, we will try and address those now. You will have to type them in the Q&A for us to address them. The slides again are here, and all of our students at King's are taught low-cost sensing and design of environmental sensors. So if you have students who are looking to go on to a BSc or an MSc, they may be interested in those programs. So we'll see if there's any questions. I don't see any that are open. So we'll give it a few minutes. And if not, then we will close. Okay, so we have how much ongoing maintenance does the station need? What we find, there are two elements to maintenance. One is, think when things go wrong. So sensors start failing, for example, and certainly, we've had sensors that have been deployed, for example, in forests for 3 years, and after 3 years in a box, even though it's completely sealed, sensors start to fail because the components have overheated or for other reasons. And so you just keep an eye on the data that's coming in, and if something fails, you pull it out, you put another one in. The other element of maintenance is ensuring that you collect good quality data by ensuring, for example, that your rain gauge is not blocked with leaves, or your solar panel is not covered in gunk. Everything degrades in the environment. Solar panels, solar pyrometer sensors, you've got to keep them clean, and you've got to to make sure that therefore they're collecting good data. Another element is calibration. Some instruments, particularly, for example, pressure sensors, their calibration changes over time. The fact that we use cheap ones means that you can replace them manually if you want, and that's not going to cost a great deal of money. They're just a few pounds each. Okay, so if there are no other questions, I would. Okay, if these low-cost sensors are handed in for early warning system detection of floods, what should be the temporal margin within which it's recommended for the first responders to be informed of? Okay, thank you. We have one organization that's building a real-time flood monitoring system in FreeStations in Romania, and I would say, well, their experience is that that they want to collect data. Most of our FreeStations collect data every 10 minutes, right? But in a flood monitoring situation, most of that data is irrelevant. You only want to collect data when the water level is high. And so you would set the sensors to just start collecting and sending data at a high temporal frequency, let's say every 10 minutes, but only when the water level is above a certain height, because otherwise you're just draining battery and using expensive, well, it's not expensive, but you're using data costs, phone data costs unnecessarily. So you would use that kind of situation, and recording, I would say, at least every 10 minutes, so that you have the capacity to respond. We don't build early warning systems ourselves, because in the end, if there's no alternative to a low-cost early warning system, fine, do it. But if you can use higher spec equipment because you're dealing with expensive floods and people's lives, that's better. It's the same reason that particles and Arduinos are never used in medical devices, right? Because they don't have the quality and reliability that really high spec equipment does. So warning systems fine if in certain contexts, but be aware of the limitations, I would say. Okay, so I think if that's all the questions, then I'll say thank you to all our speakers, and thank you for all of you attending, and do take a look at the FreeStation website if you're interested. If you're based in London, we are looking for schools where we're deploying weather stations in a funded project, so do get in touch if you're interested in that. But otherwise you should be fine with the instructions, and as I say, comment in those if anything is unclear, and we will improve them. Thank you very much.